Okay, this is exam 2 from phys101. You put your book on the seat next to you. The bus stops and the book slides off. The book remains stationary. That's not true. The book didn't remain stationary. It actually kept going with the same velocity that it had. Gravity was acting on the book, but that's not why it slid forward. It did not move, but seemed to. It kept going, so it moved. A net force did act on the book. There was no net force acting on the book. The problem is that no net force acted on the book, and therefore it kept going with the same speed that it had because of the law of inertia. From rest, you step on the accelerator of your Subaru, providing a force for 6 seconds, after which your car is traveling at 10 meters per second. If the applied force is a third F, so we have a force of 1/3 F, and we know that F is equal to ma. So if we have a third F, that means that our acceleration is 1/3 of its original value. And since v is equal to v0 plus at, if we have an acceleration that is 1/3 of its original value, to get up to the same velocity you need a time that's 3 times the original time. So the original time was 6.0 seconds, and 3 times that is 18 seconds, so the answer is D. Alright, what can you say about the force of gravity acting on a feather or a stone? Alright, while the acceleration due to gravity for both of those is the same, the force of gravity is greater for the stone, so that's D. Anti-lock brakes keep the car wheels from locking up when you stop your car. Why does this help slow the car down? Well, this was from a concept test. We know that the coefficient of static friction is larger than the coefficient of kinetic friction, so static friction is better. It has more stopping power. So you don't want your tires to slide, because when they slide, that's kinetic friction taking part. But when they roll, the tires roll, that is that static friction that's keeping you on the road. This figure shows a block suspended by 2 ropes. The ropes are attached to the ceiling at an angle of 45 degrees. The weight of the block is 100 newtons. What is the tension in the rope on the left? Alright, so I'm going to draw my vector diagram here. This is 100 newtons. Alright, we want to know what is the tension in this rope. I'm just going to look at the vectors in the y direction. Alright, so I'm going to have the y components of both of these, and then the x components are in that direction. So this y component is t sine of 45, and this y component is t sine of 45. So I have 2 times t sine of 45 minus 100 is equal to mass times acceleration, which is equal to 0. And then if I solve that for t, that is gives me about 71 newtons, 70 newtons, so the answer is A. Alright, you step on the accelerator of our car, and in 10 seconds you increase the speed from 10 to 30 meters per second. What force is exerted on the car to produce this acceleration? And there's the car's mass. So we first need to find the acceleration. We know that v is equal to v0 plus at. And our final velocity is 30. That's equal to 10 plus a. Our time was 10 seconds. So that's 20. So acceleration is 2 meters per second squared. And then we want to know the force. F is equal to mass times acceleration. That's 1,000 kilograms times 2 meters per second squared. That's 2,000 newtons. So the answer for number 6 is B. Number 7, this figure shows an elevator with a mass 10 kilograms suspended from a rope. It's accelerating downward at 2 meters per second squared. What is the tension? So here's the tension, here's the force weight, label the vectors. The sum of the forces in the y direction is equal to T minus force weight, and that's equal to ma. Put in the numbers here. T is equal to Fw plus ma, which is mass times minus 9.8, mass times 9.8 mg, plus the mass times the acceleration, which is minus 2. It's going downward. Alright, and we solve that for tension. Let's see, our mass is 10 kilograms times 7.8, 78 newtons. So the answer should be B for number 7. A 100 kilogram crate sits on the floor. In order to set the crate in motion, a horizontal force of at least 100 newtons must be exerted on the crate. So we have a crate here. You must exert at least 100 newtons in order to overcome the effects of static friction. And then you can push the crate at a constant velocity with a force of 80 newtons. So once we get it up to 80 newtons, then that's enough to overcome the kinetic frictional force. What is the coefficient of static friction between the crate and the floor? Alright, we know that the mass of the crate is 100 kilograms. If I draw the forces, this is the normal force, and then this is the force weight. So I can say then the sum of the forces in the y direction is equal to 0. So that tells me that the force normal is equal to the force weight, which is m times g. That's 100 times 9.8, or 980 newtons. So that's our normal force. And we know that the static frictional force is equal to 100 newtons, but it's equal to mu s times the normal force. So I solve this equation for mu s, and that's 100 newtons over the normal force, which is 980 newtons, and 100 over 980 is 0.1. Alright, so the answer is B for number 8. Alright, a block of mass m rests on the floor of an elevator that is falling downward at minus 9.8 meters per second squared. What is the relationship between the force due to gravity and the normal force on the block? Well, if it's in free fall, that means that it's weightless. And when something is weightless, that means that the normal force is equal to 0. It's like you're not even touching the floor. Alright, so the normal force is equal to 0. D. If you wanted to show this, here's your block. Show it in the normal way. This is your normal force, this is the force weight. We would say that N minus the force weight is equal to m times A. Alright? But our A is equal to minus 9.8. So N is equal to m times A plus m times G, which is equal to m times minus 9.8 plus 9.8, which is equal to 0. But when you're in free fall, the normal force is 0. In this figure, the block has a mass of 10 kilograms and sits on an inclined plane with an angle of 30 degrees. What is the minimum force so that the block remains in place? Alright, so I'm going to draw my force vectors. Here's my force weight. Here's my normal force. This is going to be my x-axis, and this is going to be my y-axis, and this angle is the same as theta, is 30 degrees. Now I'm going to go ahead and draw this vector diagram over here, and I'm going to resolve my force weight vector. So this is Fn, this is F, this is Fw cosine of theta, and then this is Fw sine of theta. Now let's see, I just want to know what F is. So F, if I look at the sum of the forces in the x direction, it says that F minus Fw sine of theta is equal to ma, which is equal to 0 in this case. So F is equal to Fw sine of theta. And that is equal to the mass, which is 10 kilograms, times 9.8 meters per second squared, times the sine of 30 degrees, is equal to 98, times the sine of 30, which is 49 newtons. So the answer is B for 10. Alright, in this next one, a mass of 1 kilogram on the planet Mars. The radius of the planet Mars is 3.4 times 10 to the 6 meters. So radius is 3.4 times 10 to the 6 meters. And its mass, that is the mass of Mars, is 6.4 times 10 to the 23rd kilograms. What acceleration due to gravity does the mass feel on this planet? So we want to know what is G equal to. Well, the gravitational force from Newton's universal law of gravitation is G big M little m over r squared. And we know from Newton's second law that that's equal to mg. So if we just solve this for G, we can cancel out the m's, and G is equal to the gravitational constant times the mass of the planet over the radius of the planet squared. So 6.67 times 10 to the minus 11 times the mass, which is 6.4 times 10 to the 23rd, divided by the radius squared, which is 3.4 times 10 to the 6 squared, and that gives us an acceleration of 3.7 meters per second squared. So the answer is B for number 11. Alright, by what factor does the kinetic energy of a car change if its velocity is tripled? So kinetic energy is 1/2 mv squared. So if you triple the velocity, that increases the kinetic energy by a factor of 9. Looks like on the key for this I had the correct answer is D, but the correct answer is C, 9. It increases by a factor of 9. Alright, you drop 2 stones from the same height. One stone has twice the weight of the other stone. When they reach the ground, which stone has more kinetic energy and why? Well, you drop them from the same height. So we know initially they only have potential energy, and that's equal to mgh. Alright, if they're the same height, then that's constant. But if one has more mass, then it has more potential energy. Now, as you stop them, that potential energy is converted to kinetic energy, and so the one with the greater mass will have more potential energy, and hence more kinetic energy. So the answer for this is B, number 13. Number 14, in this figure, the bead has a mass of 1 kilogram, and at point A has a velocity of 10 meters per second. So the velocity here is 10 meters per second. It goes down the slope. What is its velocity here? So at point A, our energy consists of potential energy and kinetic energy. So the total energy, which I'll call E, is equal to mgh plus 1/2 mv squared. Now at point B, that total energy is just equal to the kinetic energy, so it's 1/2 mv squared. We'll call this VA and VB. Now we want to know what is the velocity at point B. So you set these two equal to one another, because the conservation of energy says that the total amount of energy doesn't change. So you just set these equal to each other. You have mgh plus 1/2 mva squared, and that's equal to 1/2 mvb squared. Alright, the m's thankfully cancel because, well, in this case we did know the mass, but often you don't. And you solve for VB. So this is the square root of 2 times GH plus 1/2 VA squared, and that'll give you VB. And the answer there for number 14 is 14.1. Alright, a block of mass 1 kilogram is attached to a spring with a spring constant 1200 newtons per meter. So this is the mass, spring constant. Spring is compressed by 20 centimeters, so X is 0.2 meters, shown in this figure, and then released. What is the velocity of the block when it passes through the equilibrium position of the spring? So at this point, all we have is potential energy. That's elastic potential energy. Now here, the potential energy equals 0 because X is equal to 0, and the kinetic energy is equal to its maximum value. Alright, here the kinetic energy is equal to 0 because the velocity is equal to 0, and the potential energy is equal to its maximum value. Since energy is neither lost nor destroyed, we can say that the potential energy here is equal to the kinetic energy here. So that's 1/2 kx squared, that's the elastic potential energy, is equal to 1/2 mv squared. The halves cancel. Let's see, we are looking for the velocity, so the velocity is equal to kx squared over m, square root of that, and we get the answer, which is 6.9 meters per second. Well, here in this case, X was equal to 0.2, M was equal to 1.0 kilograms, and K was equal to 1200 newtons per meter. Put those three numbers in and you'll get 6.9 meters per second. That is B. For the spring in the previous problem, what is the force exerted by the spring on the block when the spring is compressed to X equals minus 20 centimeters? So that is, at this point, what is the force by the spring on the block? So the force by the spring on the block is going to be to the right. Alright, the spring is trying to push the block to the right. So F is equal to minus kx, that's minus 1200 newtons per meter, times minus 0.2 meters, and this comes out to be positive 240 newtons. So the answer to that is B. And it comes out positive just as we would expect. Alright, I always like to check that. Does it come out as we expect the sign? And yes, it does, because you see it's to the right, and that's positive. Alright, Entergy reads kilowatt hours from our electric meters. What is this a measure of? Well, a watt is a joule per second, or energy per unit time, and then when you multiply that times time, then that cancels out. So it just gives you energy, that is A. They don't care how quickly you use the energy. You can use it all on the very first day of the month. Alright, so if they charge you for power, they would be concerned with how quickly you use it. Alright, they just charge you for energy. Okay, an outfielder throws a 0.2 kilogram baseball with a velocity of 35 meters per second and an angle of 30 degrees. At the top of the ball's trajectory, what is its kinetic energy? Well, if you recall, at the top of the trajectory, the Vy is equal to 0. So its only velocity is Vx, which is V0 cosine of theta. Alright, so our kinetic energy, which is 1/2 mv squared, is equal to 1/2 of the mass, which is 0.2, times 35 cosine of 30. This entire term is squared, and that gives you the kinetic energy, which is 92 joules. Option C. A car starts from rest and accelerates to 50 miles an hour. Later it gets on the highway and accelerates to 100 miles an hour. Which takes more energy, accelerating from 0 to 50 or 50 to 100? Alright, the answer here, C. This is straight from the concept test. Looking for a change in kinetic energy, which is 1/2 m times Vf squared minus V0 squared. Alright, that's your change in kinetic energy. How much energy does it take? To go from 0 to 50, then this term goes away. Alright, and you're just left with 50 squared. But 50 squared is less than 100 squared minus 50 squared. You can put that in your calculator just to test it, but it's true. It's as you get faster and faster, you need more and more energy to go faster and faster. Alright, a uranium nucleus is at rest and undergoes fission and splits into two fragments, one heavy and one light. Which of these statements is true? Okay, this is conservation of momentum. The lighter and heavier fragments have the same momentum but in opposite directions. Alright, that is true. That comes from the law of conservation of momentum. That is that Pi is equal to Pf. Alright, so initially it has 0 momentum. So here then, the momentum in this direction has to equal the momentum in that direction so that they cancel out, so that our Pf is also equal to 0. Okay, B is not correct. The lighter object is going to have a larger velocity. C is not correct, same reasoning. And D is not correct for the same reasoning. The lighter and the heavy fragments both have the same velocity. Alright, which of these is best approximated as an elastic collision? Alright, the answer here, an elastic collision means that no energy is lost, and the only one in which no energy is lost is number 2, which is A. When you have colliding cars, you have a lot of energy lost, and when you have a baseball and a bat, you also have a lot of energy lost. Deformation of the material, sound, heat, what have you. But we generally treat collisions between particles of gas to be elastic. So elastic, remember, momentum and energy are conserved. Alright, Peter LaFleur and White Goodman face off in sudden death dodgeball match. Peter throws his dodgeball, which has a mass of 0.5 kilograms and a mass of 5 meters per second, and strikes Goodman in the head. The ball comes to rest. What is White Goodman's speed after being struck by the ball? Alright, so we say Pi is equal to Pf. Our initial momentum is equal to the final momentum. The initial momentum includes just the ball because that's the only thing that's moving. So we have 0.5 kilograms, that's the mass of the ball, times its initial velocity, alright, which is what we want to know. And then, finally, the ball comes to a rest, so its final momentum is 0. And the White-Goodman's, actually no, I'm sorry, we're given the velocity of the ball, so this is 5 meters per second. And then we want to know White-Goodman's velocity. He's the only object moving after the final situation. So after the ball hits him, the ball comes to rest, and then he starts moving. His mass is 80 kilograms, and we want to know his velocity, his final velocity of White-Goodman. And you solve that, and it works out to be 5 meters per second. So the final velocity for White-Goodman is, I'm sorry, not 5, 0.03 meters per second, which is d. The collection of particles has a total momentum of 0. What can you say about the kinetic energy of the system? Okay, for the total momentum to be 0, it means either that the objects aren't moving or that you have momenta that are moving but in opposite direction. So you have momenta, you have objects of the same mass moving in the same direction at the same speed. Alright? Or you can say that the velocity is 0, that nothing is moving. So we don't have enough information to say whether or not this is true. Alright, a cart is rolling along a frictionless track, rain is falling into the cart. What happens to the speed of the cart? Okay, well, if its momentum, which is equal to the mass times the velocity, if you increase the mass and the momentum remains constant, then the speed must decrease. So the answer for this is C. Alright, a car of mass 1,000 kilograms is traveling at 20 meters per second and collides into a brick wall. The car rebounds at a speed of 5 meters per second. The collision occurs in 0.1 seconds. What is the magnitude of the force during the collision? Well, let's see. Force is equal to delta P over delta T. Alright, the change in momentum over the change in time. And the change in momentum is PF minus PI. And the change in time in this case is just the time, and they tell us that as 0.1 seconds. Alright, so the final momentum is it rebounds at 5 meters per second. That is mass times velocity, so 1,000 kilograms. If it's rebounding, that's minus 5 meters per second, so in the opposite direction, minus 1,000 times the initial velocity, v0, which is positive 20 meters per second, divided by 0.1. Alright, and this gives us a force, if we solve for force, of 250,000 newtons. It's actually negative 250,000 newtons. The wall exerts a force that's opposite the direction of motion, so that makes sense. But I was looking just for the magnitude, so the answer is D. Which would hurt more? A 0.5 kilogram ball hits you and bounces off, or a 0.5 kilogram ball hits you and falls directly to the floor? What we don't want, rather, is the ball that bounces off of you. That's going to hurt a lot more, for the same reason up here. You see, our force is the change in momentum over time. So if our final momentum here is 0, then that makes this force less. So it's the ball that bounces off is the one that's going to hurt, because it imparts more momentum to you. Alright, and of course this is A.